Hello and welcome back. In this video we're continuing our discussion of elimination reactions. So we saw in the last video that we can get regioselectivity for elimination reactions where the Hofmann product is usually the minor product and the Zaitsev product is the major product. Well, if we have different stereochemical possibilities, then that can be a possibility as well. We'll even see in the end of this chapter where all of these regio and stereoselective possibilities can be options for different substrates. So here we have a substrate that can form, when an elimination reaction occurs, either a cis or trans product. And what we see is that the trans product is going to be the major product. In other words, let's look at this reaction. We can pull off the beta hydrogens from either of these positions, but since they are equivalent hydrogens, we're going to get no difference in regioselectivity. But let's go ahead and draw this. So remember, ET is equal to CH2, CH3. That stands for ethyl. Okay, so let's go ahead and draw this out. So we're going to pull off a hydrogen, form the double bond, kick out the leaving group, right? And so when that double bond forms, it's going to form here. It could also form on the other side. So we could have formed a double bond between those other beta hydrogens, but we would have essentially the same possibilities for products. But we have two options here. We can either get the trans product, okay, or we can get the cis product, where in this case, the hydrogens are on opposite sides, or the hydrogens are on the same side as each other. Okay, it turns out the trans product is major, and that's because the activation energy to forming the trans product is lower than the activation energy for forming the cis product. Okay, it's going to be higher, and that's because we have this repulsion between these groups. These large groups are going to repel each other, and they take up a lot of space, and therefore forming the trans product is going to be favorable. Okay. Now we're going to see in just a few minutes that we can even have a situation where we can have stereospecific reactions, whereas we can only form one product, and we're going to see why that is in just a few minutes. But it turns out, remember that we have to have a beta hydrogen in order for this reaction to occur. A lot of times we're going to have two beta hydrogens, and we can get either stereochemical outcome. But it turns out if we only have one beta hydrogen, then it may only lead to one possible product instead of two possible products, either cis or trans. Okay, in this case we only have one beta hydrogen. Okay, so here's our alpha carbon, and then at the beta carbon we've got one hydrogen that can be pulled off. Okay, remember our mechanism here. We've got a base, pulls off a hydrogen, forms a double bond, kicks out the leaving group. Okay, we've only got one hydrogen here to be pulled off, so we only have one possibility, it turns out, for our product. When our product forms in this case, we get this isomer on the left. Okay, we can figure out whether that's the E isomer, it says here. And then this isomer on the right is not formed. So let's look at why that is. It turns out that when this mechanism occurs, for this mechanism to occur, the hydrogen and the leaving group must lie in the same plane, or at least approximately the same plane. So the transition state is anti-coplanar. Okay, so that's called anti-coplanar. Okay, and so that's because when the base is pulling off this hydrogen, okay, we're forming this double bond. The leaving group is leaving in this transition state, all of these atoms have to lie in the same plane for this to happen. So we pull off the hydrogen, form the double bond, kick out the leaving group. Everything's in the same plane, so the term is anticoplanar. So if we only have one hydrogen, then in order to form that product, we need to rotate, or in order to predict the correct product that's formed, this is the stereospecific product, we need to rotate the molecule so that the hydrogen and leaving group are in the same plane and so that they are anti to each other. Okay, so they can't be syn to each other. This would be considered a syn coplanar. And we've shown that down here, or let's just say here on the left, this is anti-coplanar. So what happens? We can rotate about this sigma bond in order for the product to form. And in fact, that's what happens when this product is actually formed. All of these molecules are rotating all the time in solution, but it must be in this anti-coplanar orientation, or the rotamer must be the anti-coplanar rotamer in order for the product to form. And even if they're in the same plane but they're syn coplanar, this product's generally not going to form. Okay, it's too high energy. So the anticoplanar product is shown here on the left, and we can use a Newman projection to show that. So remember I told you when we covered Newman projections that we were only going to use those in basically one spot in this course, and this is that spot. That's why we learned to draw Newman projections, so we can predict the product of stereospecific elimination reactions. Now you only need to use a Newman projection if you have a situation where you only have one hydrogen at the beta position. If you have two hydrogens at the beta position, you can assume that you will form both stereoisomers, okay, from the elimination reaction. So we have the anticoplanar configuration on the left, and of course those are the staggered configuration because they're going to be lower energy in order for this to form. And we have the syn coplanar on the right. That's the eclipsed conformation. That's going to be higher energy, and it will deter the formation of this product. Okay, so let's look at how we can predict the product here. So again, we have the same isomer of this molecule, and over here on the left we see the anticoplanar configuration. What we're going to do is, we're looking at it head on, of course. We're going to pull off the hydrogen, form the double bond, and kick out that bromine. When we do, we're putting the double bond right between the front and the back atoms. Okay, so you can just keep that double bond in the same configuration as the groups were in the Newman projection in order to predict that product. Okay, so if you want to predict the product from the Newman projection shown here, what you do is just draw a double bond, okay, and then draw the four, the double bond's going to have four groups attached to it because it's sp2 hybridized, so each carbon will have two other groups other than the carbon next door. And so just keep those in the same configuration. So here we have a phenyl. We're going to put that phenyl here. Here we have a hydrogen. We're going to put that hydrogen here. Over on the left we have a methyl at the top. We're going to put that methyl at the same position on the double bond. And T-butyl on the left bottom, we're going to put that T-butyl here. Remember, a T-butyl group is like this thing. Okay? A phenyl group, that's equal to T-butyl. Phenyl is equal to the benzene ring. Okay? Alright, methyl is CH3. And so those are what those abbreviations mean. Okay? So I don't really like the way your book does it that much. I'd prefer just draw the double bond and then stick the groups in the same configuration that they were in when they were in the Newman projection. Now, we don't really have to have the exact anti-periplanar 180 degree bond angle anticoplanar at 180 degree bond angle. The term that's more generally used is antiperiplanar. It just needs to be about, the groups just need to be about 180 degrees from each other. So antiperiplanar is a more broad term indicating that the groups have to be about 180 degrees from each other. So even though the E isomer or the trans isomer is generally more stable because it's less sterically hindered, you have to have this antiperiplanar configuration or transition state in order to get the product. So that may even lead to the less stable cis or Z isomer, because that's the only isomer that can form, okay, if you have a stereospecific elimination reaction. So let's see if we can predict some of these products in order to utilize the information we just learned. Alright, so in order to predict the product, we're going to need to draw the Newman projection. So remember, we're going to be forming that double bond right here, okay? So we're going to, let me erase that real quick. Go ahead, just erase that. Okay, so what we're going to do is the base is going to pull off a hydrogen, form the double bond, kick out the leaving group. But in order to really predict where those R groups are going to end up, we're going to need to draw a Newman projection. So since the double bond is going to be between those two carbons I've highlighted in blue, we have to draw the Newman projection with those being the front and back carbons. So let's look at this from the right, from that orientation, okay? So our front carbon is going to be a dot, and if my eye is here and I'm looking in that direction, okay, I've got an R1 on my left, I've got R2 down and to my right, okay, and the bromine is straight up, okay. So now drawing the back carbon, okay, looking straight through to the back, I've got R1 up and to my left, I've got R2 up and to my right, and the hydrogen straight down. So this is perfect. This is in the orientation I need to perform that elimination reaction. So when the reaction occurs, I'm eliminating bromine and hydrogen from that antiperiplanar transition state. So where I've drawn a circle, I can just simply put in a double bond. All right, well, it's not a circle, it's an oval, right? And so then I'm going to attach the 4 bonds that form when you form a double bond. Now you have 4 bonds instead of that with an XP 3 hybridized carbon. So you're only going to have 4 bonds around that double bond. Now I'm just going to stick the groups where they would have been located. Okay, so R2 is going to be on the upper right, another R2 on the lower left, R1 on the upper left, and R1 on the lower left. Okay. So I'm not sure if I said that all right. So R2 on the lower right and upper right, R1 on the upper left and lower left. Okay. So for the next one, I'm going to do the same thing. So I have a slightly different molecule. The R2s are on the right side and the R1, we got R2 and R1. No, I'm sorry. This is a different stereoisomer of this molecule. Okay. So that's what the difference is here. So let's go ahead and draw that. We've got R2 and R1 on the right and R2 and R1 on the left, but they're swapped. So this is a different stereoisomer. These are enantiomers of each other, right? Because both of them are swapped. No. R1 is coming out on the left and R2 is going back on both of them. Okay, and then on the right we've got R2 coming out and on the bottom one and going back on the top one. So these are diastereomers. Okay, so looking down, so there's still different stereoisomers of that molecule. So the front carbon here, I've got bromine straight up, if I'm looking in that direction. I've got R2 down and to my left. I've got R1 down and to my right. Okay, let's change colors. So then the back carbon, I've got R1 up and to my left. R2 up and to my right, and hydrogen straight down. Okay, so when I do this elimination, I circle or oval, make an oval around the hydrogen and the bromine, so that's where I'm going to put my double bond, and then I attach the 4 bonds that go on that double bond. The R2 is on the upper right, R1 is on the lower right, R1 on the upper left, R2 on the lower left. All right, and so we end up with a different configuration for the product. Okay, so because we started out with a different stereoisomer. Now here we have an example of a substrate that has 2 beta hydrogens, and because it has 2 beta hydrogens, we can get both stereoisomers as possibilities. We can have both the E and the Z isomer of these molecules. So this is called stereoselective instead of stereospecific. If we only have 1 beta hydrogen, then we get a stereospecific elimination reaction. So elimination occurs when both the alpha and beta carbons are actually stereocenters. When it'll be stereospecific when the alpha and beta carbons are stereocenters. I'm sorry, I don't think I said that right. Because otherwise it wouldn't matter. Alright, so stereospecific versus stereoselective. So stereoselectivity means that we've got our starting material here. We're going to have 2 possibilities for products, major and minor. Stereospecific, we got the starting material can only give us 1 possible product. So we can look at an example of this elimination on a ring. Okay, so we can only get the elimination when the chlorine is in the axial position and antiperiplanar to a hydrogen. When the chlorine is in the equatorial position, we don't get elimination. So it has to be able to achieve the axial position for the leaving group. The leaving group has to be able to enter the axial position in order for this elimination to occur. Okay, and it also has to be anti to a hydrogen. Okay, so let's look at this example here let's call these A and B. So for molecule A, we've got a chlorine that has 2 hydrogens anti to it. Okay, it's anti because the chlorine is on a wedge and the hydrogens are on dashes. So they're anti to each other. They're on opposite sides of the ring. They're like in trans to each other on that ring. And so because of that, we can actually get an elimination reaction to occur. And it can actually occur on either side. So if it occurred on the right side, between this hydrogen and let's do a change of color here. Between this hydrogen and chlorine, we would get the methyl, nothing happened to the methyl. Okay, the chlorine is eliminated, and we get this product. If it happened to this hydrogen and the chlorine, okay, I thought I changed colors, sorry. This hydrogen and the chlorine. Then now we have the methyl at the double bond. Okay, so we could have either one of those products. Both of those will occur. Okay, and so this one on the left is more substituted, so that's probably going to be our major product. The one on the right is less substituted, so it'll be a minor product. Now let's consider molecule B. The chlorine is only cis to the hydrogens. It's not trans to any hydrogen, and therefore, if we do an elimination, we get no reaction because the chlorine, the leaving group, cannot achieve an antiperiplanar configuration to any hydrogen. So let's think about this possibility here. We have only one product formed on the top, okay, and that's this product on the right. So let's call this molecule A, and that's because the chlorine is trans to the T-butyl group and cis to the hydrogen that is at the T-butyl group. So the only beta hydrogen that we can pull off is going to be these two, one of these two hydrogens over here on the left, the one that's trans, right? One of them is coming out and one of them is going back. So that the one coming out is the one that's going to be pulled off. So this is molecule A. All right, and so, but on the bottom molecule, let's call that B, we've got a chlorine coming out, and therefore there's a hydrogen going back at that T-butyl group. We can get an elimination from pulling off that hydrogen because those are trans to each other, the chlorine and the hydrogen. So we can form that antiperiplanar transition state and form this product on the right. We can also pull off the hydrogen that is going back on the left and get this product, the first product, okay? So this one on the top, it says this rate is slow, and on the bottom it says this rate is fast. Okay, so let's think about why that would be. It's because remember that T-butyl group is going to want to be equatorial. Okay, and in order, we could draw if you draw the chair configuration of this molecule where the T-butyl group is equatorial, then the chlorine is also going to be equatorial. And so that it takes a lot of energy to get that chlorine into the axial position. But here on the bottom molecule, when the T-butyl group is equatorial, the chlorine is going to be axial, and that's going to force that reaction. That's going to force the chlorine into the axial position where it needs to do this reaction, so that reaction is going to be much faster. So we have to consider a lot of factors when we're drawing E2 reactions, and also we're going to see at the end of this chapter that we even need to consider competing pathways like SN2 or SN1 or E1 reactions, which we haven't even talked about yet. And so this chapter has a lot of parts to it, and there are a lot of competing pathways for products. We need to consider for E2s whether the substrate will react stereospecifically or whether it will react stereoselectively or regiospecifically. So or regioselectively, where we have a different regioisomer, whether we have a different stereoisomer. So we have to consider all of these things. Okay, so we need to do a lot of practice. Okay, so let's look at problem A. All right, so let's look at problem A. So we've got for A, I think I'll redraw it. Well, I don't really have to do that. It's not that big, Okay, so for A, I've got the alpha carbon bearing the bromine. I don't have a beta hydrogen on the right. I have two beta hydrogens on the left. It means I only have one regioisomer. But since I have two hydrogens at that position, so in other words, I can only form the double bond between these two carbons, right? So I don't have I don't have regio isomers to worry about. But since I have two hydrogens, I can form both the E and Z, or cis and trans isomers, okay? So in other words, this bromine is going back. So if I eliminate the hydrogen that's coming out, those will be anti to each other. then I'll have the same isomer that I have as I've drawn it here, okay? But if I rotate about that center bond, okay, then I would be pulling off the other hydrogen, because now the bromine is, let's just draw that rotamer. Now I rotate about that bond. Okay, so now the bromine is now coming out at me. The hydrogens didn't move. So now the hydrogen that's going back is going to be eliminated and the bromine is coming out, okay? And so that's going to give me this product, this stereoisomer. Which in fact, because I have hydrogens, I didn't mean to draw that as a, okay. Because I have hydrogens, this is the cis isomer. On the left we have the trans isomer, okay? Because we have hydrogens trans to each other. So which do you think will be the major product? This trans one is going to be much more stable because it's the major product, because it's, these groups are large. The T-butyl group and the phenyl group are large, so they're going to be pushing each other away in the transition state. So the trans product will be major. All right, so let's look at B here. So in the configuration, in the configuration as it is drawn, we have a hydrogen going back and a bromine going back, and so we can't eliminate that way. We have to have that hydrogen coming out. So we really don't even need to draw a Newman projection here. We can just simply rotate about this bond. So for B, the rotamer that we want to use for the elimination is going to be the one where if we rotate about that bond, the bromine is now coming out and the methyl group is also coming out on the alternate carbon. Now the hydrogen's going back and these guys are antiperiplanar to each other. We can do the elimination. So the product is going to be the one with the double bond between the two carbons as shown, which is the cis configuration. Okay, and we could have predicted that by drawing the Newman projection. Let's draw a Newman projection. Let's draw a Newman projection as shown here in the rotamer shown, okay? So on the front carbon, I've got hydrogen up and to my left, bromine up and to my right, T-butyl straight down. On the back carbon, I've got methyl to my left, hydrogen to my right, and phenyl straight up, okay? Now I can't eliminate bromine and methyl, okay? I need the hydrogen on the blue carbon to rotate over here. So I need to rotate that. And when I do, I'm going to keep my front carbon in the same configuration. So the front carbon is bromine, hydrogen, T-butyl. The back carbon is, now I've got the hydrogen over here. So that moved the methyl to the top. So the methyl moved up here and the phenyl moved over here. So now phenyl is over here. So I'm doing the elimination from that hydrogen and the bromine on and the hydrogen on the alternating carbon. So to draw the product, I'm simply going to put the double bond where I drew that oval, okay? And I'm going to keep the other groups the same. Methyl up here on the top right, phenyl on the bottom right, hydrogen on the top left, T-butyl on the bottom left. Okay, so that will be our product, which is the same, you see, as what I have drawn up here. I've got the methyl and phenyl on the same carbon, I've got the T-butyl on the same side as the phenyl. So those are the same products. Okay, so you really didn't have to draw a Newman projection here. You could have just predicted that I needed to rotate in order to eliminate anti from the bromine and the hydrogen. So let's look at this last one here. I've got a hydrogen coming out and a methyl going back. So that's actually perfect. I'm going to draw the product for C over here on the right. Let me draw it in a different color so it'll be a little bit different. Okay, so that's perfect. So I can just draw that same configuration of the molecule and just putting that double bond right there. Okay, right there where I'm doing the elimination. All right, so we've got a few more examples here. Predict the major and minor products for each of the following E2 reactions. Okay, so we do have competing reactions here. So for A, competing possibilities for products. In other words, we can have regio and stereochemistry. All right, so this is challenging. So for A, I can have the possibility where I eliminate from the beta carbon on the right. Okay, so if I do that, I will have phenyl, let me see here. Isopropyl group is going back. We didn't change anything there. So that's the product. So this is one product. That's going to be a Hoffman product. All right, the other possibility is we can't have the same rotamer because we've got chlorine and hydrogen on the same side. We're going to have to rotate. If you want, you can draw a Newman projection here, but I'm not going to do that. I'm just going to simply say, I know I've got to rotate about that bond to bring that chlorine back into anti to the hydrogen. Okay, and when I do that, it's going to make that methyl group cis to the phenyl group. Okay, and my T-butyl group then will be, I'm sorry, my isopropyl group will be up. Okay, so this is going to be the stereospecific product for elimination at the left beta carbon. Okay, so these are the only two products that are possible here. Which is going to be major? Well, the Selective product may be major, probably will be major because it is the more substituted product. Now, the Hoffman product is less substituted, but we do have 3 hydrogens there, so it's kind of hard to say which would be major and minor. Probably have to see that distribution, but without that, I'll say, I'm sorry, major on the left, minor on the right. Okay. All right, so for B, we've got a hydrogen going back at the methyl group, and that's going to give us the Selective product from that bromine. We're eliminating anti here. All right, and so that's going to be our Selective, and probably the major product. Now, if we eliminate on the left side from one of those hydrogens, okay, which is going to be the hydrogen going back, we haven't done anything to that methyl group on the right. Just put a double bond here. That's the less substituted product. That's the Hoffman product. And that's going to be the minor product. All right, so for C, we've got an isopropyl group on the left that's going back and a hydrogen that's coming out on the left. We can't eliminate from that hydrogen because it's not anti to the bromine. The hydrogen on the right is in fact anti, and therefore for C, we have this elimination product. We didn't do anything to that isopropyl group on the left. This is our only possible product. For D, we can eliminate, we can get a Hoffman product by eliminating at this carbon here, one of those hydrogens. Okay, or we can eliminate inside the ring, and it doesn't matter which one you pull off there. Okay, so we can get, I'm going to erase that. Looks like I just rotated it a little bit. Okay, so we can eliminate here, and if we eliminated over here, so we eliminated the carbon down here, if we eliminated at the top one, it wouldn't matter, we get the same thing. So this is the Ch7 product, and that's going to be our major product for this example. Alright, thanks for watching, and in the next video we're going to begin our discussion of SN1 and E1 reactions.